Okay, very good. My name is Whitham Reeve, and most people call me Whit. I'm going to be talking about HF Aurora radio reflections that I've received at my observatory here in Anchorage. I have some introductory comments to make. I'm going to talk a little bit about the concepts of Aurora radio investigations, and then we'll go into some of my observations. And there's a long paper in the proceedings that describes in a lot more detail than what I'm going to go into here. This is an image of, this is a map of Alaska, and my Anchorage Observatory is down here in South Central Alaska. And I've also built another observatory down in Coho, which is about 100 kilometers, maybe 125 kilometers southwest of Anchorage. And then most recently in 2019, I built another observatory within an observatory up at the HARP facility near Gakona, and that's about 300 kilometers to the northeast of Anchorage. But all of the observations that I'm talking about here are from Anchorage. What I'm looking for at these places is I cover quite a range of frequencies, but most of it is close to home within the solar system. I do a lot of solar radio, VLF through the UHF frequency bands. I've been doing Jupiter radio, which is in the HF band, and I'm most interested in high latitude radio propagation, and that's how I got into the Aurora radio reflections. And if you attended the SARA conference last fall, I described meteor trail radio reflections that I had received at Anchorage, and I went back and reprocessed that data and came up with the Aurora part of that. And I also do a lot of geomagnetic type observations using my SAM-3 magnetometer. And I have an installation at Anchorage right now with the SAM-3 that's been in service for about 14 years now. And I'm going to be building one up at the HARP facility here this summer, as soon as the snow melts. I still have about 3 feet of snow out in my yard here, but it's melting fast. Okay, Aurora radio reflections. There's a lot of names that have been given to this. Radio Aurora, Aurora radio, Aurora scattering, Aurora echoes, Aurora reflections. Those all mean the same thing, but not to be confused with actual radio emissions from the Aurora. And these are called Aurora kilometric radiation or Aurora kilometric emissions. So I'm talking about the radio reflections from the Aurora itself. This is kind of a artistic representation of what's going on here. The Aurora is shown by these bright rays here in the background, and these rays follow the Earth's magnetic field lines. And when there is a magnetic disturbance of some type that produces the Aurora, there's clouds of electrons that are formed. The electrons are trapped by the magnetic field lines, and so they form in clouds. And so there's an increased electron density in this region here that I'm showing in blue. And if you have a transmitter down here in the lower left shown in green that's transmitting a radio wave toward that Aurora, there's going to be some of that energy reflected back down to a receiver shown here on the lower right. And this is a bistatic radar type setup where the transmitter and receivers are located at different places. So this is basically what we're looking at. And I'm going to be going into some detail about how this all works. Now, there was a lot of early investigations made about aurora radio. Interestingly, it was amateur radio operators that first started reporting aurora effects on radio propagation. And the earliest I could find was an article in QST magazine from 1926. And then after that, through the 1930s and 1940s, there was a lot more discussion in the amateur radio trade magazines at that time about aurora effects on radio propagation. And this inspired the U.S. Army Signal Corps to look into this. And in fact, they funded early studies that basically read all the trade magazines, the amateur radio trade magazines, and then compared those reports in the magazines to visible aurora observations taken at the same time. And it was these studies that were funded by the U.S. Army Signal Corps that confirmed the coincidence of radio aurora with a visible aurora. Now, that took off so that in the 1950s and 1960s, there was a lot of work done on this with both bistatic and monostatic radars. And the monostatic radar has the transmitter and receiver in the same location. And the diagram shown here shows the basic configuration. You have the transmitter and the signal is then going to the aurora. And if the geometry is good, you'll have a reflection down to a receiver here. And it is the bisector of the angle between the transmitter and the receiver. If that bisector is aligned properly, then all of this will work. If it's not aligned properly, you won't receive the reflections. Now, one of the things that was noticed in these early investigations is that the received signals had a really high fading rate, 200 hertz fading rate at a 50 megahertz signal. Now, all of the radio amateurs here in Alaska that I've talked to about aurora radio reflections have said it's really an impediment to communication. The voice communication is almost impossible, if not completely impossible. CW can be made to work, but it's not a reliable method of communications. Now, there's been a lot of speculation as what causes the fading rate of aurora radio reflections. It could be the change in absorption in the D layer, for example. Could be interference between wave components, so a constructive and maybe destructive interference. Changes in the electron density or the drift movement of those field-aligned electron clouds that I mentioned earlier. I don't know from my observations which of those apply, maybe all of them. They found also that directional antennas gave the best results when pointed north toward the aurora. So this indicated there was some aspect sensitivity. So in other words, if I pointed my transmitter to the east, for example, toward aurora, maybe it was overhead, and I pointed east, I wouldn't get a reflection. But if I pointed that same transmitter north, then I would get a reflection. So that led me to believe that one of the stations that I use for a transmitter, for a beacon transmitter, is the one that I'm receiving. And I'll show you a drawing of that here in a minute. Polarization did not change. This was noticed in the early days that if they sent, say, vertically polarized, it would be reflected back as vertically polarized. Now, there was another thing that was noticed is that although radio aurora and visible aurora occurred at the same time, there was no requirement that one had to be present in order to observe the other one. So if you saw a visible aurora, that didn't guarantee that you were going to see radio aurora or vice versa. But there was a high probability that you would see one if you saw the other. And in fact, that's one of the key elements that I used to determine that what I was seeing was, in fact, radio aurora. Another thing is that radio aurora and geomagnetic activity are well correlated. And this was another kind of a key checkbox for me, is that I noticed that when there was any significant amount of geomagnetic activity, that's when I saw certain spectral signatures on my receiving equipment. No reflections were received when the aurora was directly overhead. So in other words, if you pointed your transmitter up and you were far enough north, say, where the aurora was directly overhead, then you wouldn't get a reflection. But if you pointed that transmitter at the horizon to the north, then you would get reflections. The aurora reflections occurred in the early investigations when visible aurora was below about 110 kilometer altitude. So that's in the neighborhood of the E region of the ionosphere. And there's a lot of action that goes on there. The meteor trail reflections occur at about the same altitude. You have your aurora reflections there. You have sporadic E communication and so on. Another thing was that visible aurora was most often evenly distributed about local midnight, while radio aurora peaked before midnight. And that's one thing I noticed in my observations, is that almost all of my observations occurred before midnight. Less than 1 parts per million of the energy incident on the aurora was reflected back. So those were made by radar measurements where they knew or could calculate the radio flux density and then the received amount, and it was about 1/1,000,000th of the power. There was some drift or Doppler frequency shifting noticed, and they recorded radial speeds of up to approximately 1,000 meters per second. Most were below 600 meters per second. In my case, because of limitations in my spectral recorder, then I could see up to 200 meters per second Doppler shifting in the reflections. So what we've got going here is we need to know that visible and radio aurora are different manifestations of a similar process. Visible aurora is caused by atomic and molecular excitation that produces light, whereas radio aurora is caused by ionization of the atoms and molecules and reflection of radio waves. And there's a lot of deep detail in that paper that's in your proceedings. If you're really interested in this, you can go to that, and you can also get some good references out of that as well. Now, I mentioned earlier that visible and radio aurora do not necessarily occur together, but there is a high probability that if you have one, you're going to have the other. However, on the other hand, radio aurora has been recorded at very low latitudes, down to 25 degrees. That's almost equatorial, whereas visible aurora is extremely rare down there, even during really strong geomagnetic storms. A radio aurora can occur during daylight when visible aurora cannot be seen. There may be aurora, but you can't see it in daylight because it is so dim. They share a lot of characteristics between visible and radio. Aurora. They're observed in the same geographic and height regions at high latitudes generally, and altitudes of in the neighborhood of 100 kilometers. They correlate with geomagnetic activity. They have similar statistics of observation and motion, vary in similar manner annually and over solar cycles. And they also show 1 or 2 or 3 daily variations of peak activity. And these are called substorms, very familiar in geomagnetic studies and observations. But I'll show you some examples of that here in a few minutes. So here's what we have. I have an elevation and an overhead view of schematically of what's going on. For me, I believe the beacon transmitter that I am using is in Hawaii, and that's WWVH at 15 and 20 megahertz. And you'll see that the distance from Hawaii to Anchorage is about 4,400 kilometers. And so that indicates that there's skywave propagation involved here. It's not ground wave for sure. It's just too far for that. And then that radio wave or radio signal from the transmitter in Hawaii has to travel another 500 or 1,000 kilometers north of me, where the Aurora is, and that's close to the horizon. And then it's reflected back to me at Anchorage. And so that's a two-dimensional look from an elevation point of view. From an overhead point of view, you can see that the transmitter might be offset here to the west of my receiver in Anchorage. And so the geometry of this propagation has to be just so. Everything has to line up in almost a perfect manner in order for that signal from the transmitter to be reflected off the Aurora and then back down to my receiver, another 500 to 1,000 kilometers back to the receiver. So I've already mentioned that we have a bistatic receiver radar that is the configuration that I use. The transmitter and receivers are fixed. That's the static part, but they're separated by some distance, and that's the bistatic part. And if you look back at that previous drawing, whoops, sorry about that. I hit the wrong button on my keyboard here. There we are. If you look back at this drawing here, you can see that the transmitter and receiver are separated by over 4,000 kilometers. And there are two possibilities, since my receivers are tuned to 15, 20, and 20 megahertz generally, or at least they were in 2020 when I did the study. The two possibilities are WWV near Fort Collins, Colorado, and WWVH in Hawaii. And I'm fairly certain that it's WWVH that I'm receiving, because if you look at this map here, you can see that the route or the propagation path from Hawaii to Anchorage is almost exactly north-south, whereas the path from WWV in Colorado is east-west. So in order to get that, the aspect ratio where the reflection region is north of the transmitter, then I believe that it's coming from WWVH and being reflected in northern Alaska, close to the horizon, back down to Anchorage. And so this is the presumed aurora reflection region that I use. It's non-line of sight. I've come up with this concept of a virtual transmitter that's based on the hop points of the signal coming from the transmitters that are so far away. They could either be here in the ionosphere at a refraction point, or down here on the ground as a reflection point to get up to the aurora and then back to my receiver. There's the usual variations with solar activity, because the aurora is tightly coupled with geomagnetic disturbances, geomagnetic disturbances are tightly coupled with the sun. So those variations occur in radio reflections as well. As far as instrumentation goes, I have a setup that I started building back in 2008, and I really got into got serious about doing meteor trail and aurora reflections back in 2014, and I dedicated one receiver to that ran 24/7 and recorded with Argo software on a PC. But in my setup, I've got a log periodic antenna, which it's an 8-element antenna. It's not very directional. It's got a wide beam width. And so it doesn't really matter where it's pointed. And that goes through a multi-coupler where I can connect up to 8 receivers. And the audio output of the receivers go through a 6-port analog audio mixer, and from there into the line-in port of a sound card. So what it is that I'm actually recording the demodulated signal that these receivers are picking up. The Argo software, if you're not familiar with it, it's really a narrowband horizontal spectra waterfall image that it produces. And down here on the lower horizontal scale is the time scale. My plots are typically 12 to 13 minutes wide. And then on the vertical scale on the right-hand side, you see the frequency. And you can see that I only cover a plus or minus 20 hertz bandwidth with this. It goes from approximately 980 up to 1020 hertz. So this is the demodulated signal that is being recorded here. My receiver is tuned, for example, to 15.001 megahertz, and it's set to lower sideband mode, so that when that carrier comes in at exactly 15 megahertz from WWVH, it's demodulated as 1,000 hertz. So it would show as a line here in the middle at 1,000 hertz. And then we have the indications in the spectra of the reflections themselves. As far as the geomagnetic part of this is that I use the magnetometer in conjunction with Argo to tell me that I'm seeing aurora reflections. So if I see geomagnetic activity at the same time that I see something like this, then I know I've got a good possibility that it's radio aurora. And the SAM magnetometer produces a magnetogram that's shown here. Time is on the horizontal scale. In this case, it's a 24-hour scale. And then on the vertical scale, I have a normalized magnetic induction or magnetic flux density that's shown here. And on a quiet day, these traces are just lazy across the 24-hour period. But if there's any kind of geomagnetic activity, then I see these wild variations here. And that's when I noticed that the Argo spectra starts showing some interesting indications. So let's go and look at some of the observations that I've made. And this is all from 2020 data, same as the meteor trail radio reflection paper that I presented last year. One thing that I've noticed is that all Aurora radio are accompanied by geomagnetic disturbances. And I've noticed that it's the rate of change of the geomagnetic disturbance is more important than the amplitude change. So if it's a rapid change, then I'm going to see some type of activity on the Argo spectra. So geomagnetic storm conditions are not required, but there has to be some kind of a disturbance. And that translates into a K index of 3 or greater. The patterns that I see sometimes are just like in a visible aurora substorms, where there's a relatively quiet condition followed by an active condition and then a return to quiet condition. This may occur a couple times per night or maybe even 3 times per night. The signals that I receive are very, very weak. And if I listen to the audio, it sounds like a flutter or a rapid hash or buzz-like sound. And if there's any voice there, it's impossible to actually understand what the voice is. Sometimes I will be able to verify the source of the signal that I'm receiving, what I would call the direct signal at Anchorage from WWV or WWVH. In other words, I hear a male voice for WWV and a female voice for WWVH, but that's not a reflected path. That would be the path that from that transmitter into Anchorage, non-reflected, and I can sometimes make out that voice. Most of my observations or my detections were in the dusk to midnight sector. So here's the Earth over here on the right-hand side. It's moving through space around the sun downward. The sun is off to the right. And most of my observations that I have from 2020 occurred in this sector here. So after sunset, but before midnight. And I did see some during daylight hours. I did see some in the midnight to dawn sector shown here, but predominantly they were over here in the dusk to midnight. There's 2 types of signatures that you will see on the observations I'm going to show here in just a minute. There's the bright thin traces with very rapid frequency shifts cover the full frequency span of the Argo plots. In other words, of the full 40 hertz that's shown on the plots. And some of them may have exceeded that, except they just weren't recorded by the setup that I had for Aurora, for Argo. And I'm calling those discrete Aurora radio. There's also going to be some bright diffuse traces that with rapidly drifting frequencies, the frequency shift is not as great as the discrete, and I call these diffuse Aurora radios. Oh, and one other thing is when I see discrete, I may see, say on a 12-minute Argo plot, I may see both discrete and diffuse, but they don't overlap. Generally, they don't overlap. The Doppler frequency shifts that I'm seeing are limited to plus or minus 20 hertz, as I mentioned before, and that's because of the way I have the software, the Argo software set up. There's appear to be some that could go higher than that, but with the 20 hertz plus or minus 20 hertz limitation, that would correspond to a few hundred meters per second radial velocity of those electron clouds, or the changes in absorption or whatever is causing that frequency drift. And you'll notice that a lot of my observations show a bias toward negative Doppler frequency shift. Now here's an example of a quiet to active to quiet situation. This was on the 9th of January, 2020. Over here, there's no reflection whatsoever. And if I had shown more of these Argo plots before this, it would have been very quiet, just dark. And then we see an increased intensity. And these are Doppler radio shifts, frequency shifts that you're seeing here. And then it dies off again. And for the rest of that night, I believe it had died off completely. So it was just this short interval from about 0700 to 0742 or so UTC. And these Argo spectra plots that you see here have been spliced together. So there's a 48-minute stretch of 4 Argo plots. 4 12-minute plots give you 48 minutes. Now I'm showing up here the SAM magnetometer readout for that day. And if you look at 0700 or so, that's this region right here. So you can see the magnetic field is just starting to get active at that time when this occurred. This lower plot is a keogram that shows visible aurora activity at different locations across Canada and Alaska. And I use those not as a checkbox, but as a kind of an aid in identifying whether or not I was seeing aurora radio. Now here's another one that shows what I call a double path, and it occurs about 1000 to 1020 UTC, and that is right here. These little blips that you're seeing right here in the X and Y components is what I believe had caused this. And you can see that we have one path here that's kind of a more or less straight horizontal line that gets brighter and then tapers off. But then we also have these heavily Doppler shifted indications here. And so that may be a different signal. For example, this might be coming from WWV, a non-reflected path. And then this lower one here might be WWVH being aurora reflected. Here's this one shows both discrete and diffuse aurora, 0600 to 0720. So that would be this region right here on the magnetogram, where you can see there's been some rapid changes, but the K index is not super high. K3 is basically an unsettled condition, but they were fairly rapid changes. And you can see that we have this discrete aurora that's heavily Doppler shifted over here on the left side of this plot. And then it gets much brighter, but it's a diffuse plot from then on. And we do see a little bit overlapping of the discrete, and that's not really that common, at least in my own observations. But you can see there's more discrete reflections over here on the far right of this particular plot. Here's a good example of both discrete and direct. So this bright line, horizontal line that you see here would be a direct path from one of the beacons, either WWV or WWVH, and that would be coming directly to my receiver. And then these heavily Doppler shifted indications that you see here and over here on the right and over here on the left, those are the aurora reflections. Now, this signal that you see here, this very weak signal that's wandering through here, I'm not real sure what the source is of that. That could be anything. These occur at about between 620 and 712 UTC. So that would be in this region right here. And there's not much going on magnetically at that time. So that's one of the few observations that doesn't really show a lot of magnetic activity associated with it. Now, here's an example of a daytime aurora. You can see there's a more or less direct path, but also some diffuse type aurora. Here, right smack dab in the middle is some diffuse. Over here on the left is some discrete. And this is roughly 0400 to 0510. So that would correspond to the geomagnetic activity shown right here. And this was in June, so there would be no visible aurora because of the daylight. Now, I mentioned earlier that aurora occurs in what are called substorms, where you'll have quiet conditions followed by an active condition, followed by a quiet condition, and that cycle may repeat a few times. And these two plots here are spliced Argo plots, and you can see that there's a little bit of this plot here. You can see there's a little bit of discrete radio aurora. It gets quiet and then flares up again over here on the far right of this. And this plot here ends where this one begins right here. So you can see it, the flare up of the radio aurora, and then it tapers off again and then flares up. So this is a good example of a substorm, and these correspond to the time right in this neighborhood right here, from about 0600 to almost 0900. So that would be 600 is right here. So it's going to be these geomagnetic indications that would correspond to that. Okay, so those are my observations, and just a little bit of discussion, and then I'll be done. I'm fairly certain that because of the propagation geometry that's required, that WWVH is the beacon that I'm using. It's 4,400 kilometers away, and in order to get the low elevation angle reflections, the reflection region is in the neighborhood of 750 to maybe 1,000 kilometers north of Anchorage. Now, 1,000 kilometers north of Anchorage would put it on the north coast of Alaska. And so that part of it, I think, works out okay. Most of my reflections were detected before local solar midnight. I did see a few in the midnight to dawn sector, so that'd be after midnight, and that I did see a few during daylight hours. Now, one of the things that is really important for these types of observations is that there has to be favorable HF propagation from the transmitter to the aurora, and then favorable propagation back from the aurora to my receiver in Anchorage. So that doesn't occur all the time. Even if there's a magnetic storm, the propagation geometry may not work out. So there was a lot of times in 2020 when I saw nothing at all, even though I know there was visible aurora activity. Now, one of the things that came out of this is that my radio aurora detections were most often before local solar midnight, in agreement with those early results that I mentioned at the beginning. There was some variation of that, but by and large, it was before the local solar midnight. There was other consistencies with those earlier observations, including high correlation between the radio aurora and geomagnetic activity. The radial speeds that I found by Doppler frequency shift calculations were in agreement. High fading rates were in agreement, and so on. Where we diverged a little bit, though, is that the Doppler frequency shifts that I saw in 2020 were biased toward negative values, with most detections prior to local midnight. But the early observations indicated that detections prior to midnight had a positive shift. So I haven't been able to resolve that, but maybe more investigation would get us there. So another thing that was important is that I noticed is that the gradient of the magnetic change was more important than the amplitude of the magnetic change. So in other words, if you had a sharp change in the magnetic field as measured here, then I would have a higher probability of seeing radio aurora as opposed to amplitude change. Okay, so that's it. And if you have any questions, I can see that I'm out of time. If you have any questions, put them in the chat, and then I can answer them over the next maybe half hour or so.